In this video, we will introduce the concept of continuity. We say that the function f is continuous at a point a if the limit as x approaches a of the function is simply the function value f of a. Now, this seemingly innocent statement really requires that three things must be true. We first need the limit as x approaches a of the function to exist. As we've seen in previous examples, the limit will not always exist. We need the function value to be defined. And additionally, we need that those two numbers are the same. Now, from a graphical perspective, let me just give an illustration of this. So what we know is that as we approach the value a, the limit has to exist. So if we're thinking about this graphically, whatever is happening, or whatever our function is approaching from the left, our function has to be approaching the same thing from the right. So we would think maybe this number L would be the value of the limit. Now note, when you're taking the limit, you're not necessarily concerned with what happens at a, just what happens at inputs close to a. The next part tells you that the function value at a is defined and it is equal to the limit. That is, this gap we had in our graph is now filled in. So from an intuitive perspective, what continuity really means is that we can sketch our curve without lifting our pencil. So that's really, not a technical definition, but it's just the intuition. We can sketch the curve without lifting our pencil. And that will help us in terms of recognizing continuity from a graphical perspective. Now, if any of these three things fails to be true, we say that f is discontinuous at x equals a. So let me draw several pictures that would illustrate this. So for example, at a, we could have that the function value is defined there, but the limit does not exist. So in each of these graphs, f of x is going to be the graph. So in this case, the limit as x approaches a of f of x does not exist. The reason the limit does not exist is we're getting one thing to the left of a second thing to the right of a. Additionally, we could have that the function is undefined, but the limit exists. That is to say, my function might be something that looks like this. So in this case, the limit would exist. It would be whatever would correspond to that number L, but the problem is f of a is undefined. Lastly, it could be the case that the limit exists, like it does in this previous example, but the function value actually could be defined, and it could be some other number. So we would have L being the limit value, f of a corresponding to the function value. So in this third graph, the limit as x approaches a of f of x exists, but it's not equal to the function value. So these are the three illustrations of what it means, or graphically, how we can recognize when a function is discontinuous at x equals a. Either the limit does not exist, the function is undefined, or the limit is not equal to the function. So let's indicate where the given function f is discontinuous. While investigating this graph, I'm seeing 3 points that are jumping out at me. So the first would be what's happening at x equals minus 4. So it is discontinuous at x equals minus 4. And the ideal solution would be something that gives a reason. And the reason it is not continuous is because the limit as x approaches minus 4 of our function f does not exist. The reason this limit does not exist is because it's one value from the left and a second value from the right. So the limit itself will not exist. The second point where I'm seeing a discontinuity would be at x equals 2. And it is for the same reason as above. The limit as x approaches 2 of the function does not exist. You get one value to the left of 2, but a second value to the right of 2. And lastly, I'm seeing a problem at x equals 4. The reason being is we just have an open circle for our function, and we have no closed circle anywhere. So the reason it is discontinuous at x equals 4 is because f of 4, the function, is undefined. And if the function is undefined at a point, it is not able to be continuous at a point. So a very similar type of problem, indicate where the function f is discontinuous. And I'm once again seeing 3 problem points. So the first would be at x equals minus 2, where at x equals minus 2 it looks like the limit exists, and from a graphical standpoint it looks like that limit would be 3, but the function value is defined to be the number 5. So in this case I'd say x equals minus 2 because the limit as x approaches minus 2 is not equal to the function value. And what are those values? Just to note, 3 is the limit, 5 is the function value. 3 is not equal to 5, so the limit is not equal to the function value, discontinuous. Similarly, at x equals 1, this is discontinuous because the limit does not exist. You have one limit value from the left, a second from the right. So the limit as x approaches 1 of the function does not exist. And lastly, if we focus in on x equals 4, we see that the graph has what appears to be a vertical asymptote, which means the function is undefined. So x equals 4 is a point of discontinuity because the function f is undefined. So we really see all 3 types of discontinuities appearing in this example. A point of discontinuity because the limit does not exist, because the function value is undefined, or because the limit is not equal to the function value.